So last time we saw that the PI regulator, or its slightly more elaborate brother, the PID regulator, was enough to make the cruise controller do what it should do, which is achieve stability, tracking, and parameter robustness. Today I want to talk a little bit more about PID control. And the reason for that is this regulator is such an important regulator or controller that's out there in virtually every industry you can think of. There is a PID regulator going on underneath the hood in almost all controllers. And there are really three knobs you can tweak here. One is KP, which is the proportional gain. The other is KI, which is the integral gain. And then KD, which is the derivative gain. And I want to talk a little bit about what are the effects of these gains. Well, first of all, P, as we saw, it's a contributor to stability in the sense that it makes the system, not guaranteed, but it's helping out make the system stable. And it's making it responsive in the sense that you respond if you click or press 70 miles per hour on your cruise controller, it drives the system towards that value. I'm calling it medium rate responsiveness because it's not super fast, and the speed, in fact, the rate of responsiveness is a function of how big KP is. But as we saw, it wasn't typically enough to achieve tracking. Well, the I component is really good for tracking. And in fact, if your system is stable, then having an I component is enough to ensure tracking in almost all cases. It's also extremely effective at rejecting disturbances. So the integral part is a very effective part to have in your controller. Now, it's much slower in the sense that you have to accumulate over time errors to respond to them because it's an integral. So it responds slower, and there is a little bit of a warning I need to make there. By making KI large, you may very well induce oscillations. So this is not, oh, I'm going to pick all of them a million and go home. No, you have to be a little careful in how you actually select these gains. Now, the D part, well, since it's not responding to actual values, the error values, but the changes in the error values, it's typically faster responsiveness. So something is about to happen while the rate is changing, so the derivative part kicks in typically faster. Now, there is a little caveat to this, and that's the derivative is sensitive to noise, because if you have a signal that's noisy, then if you compute the derivative of that signal, you're going to get rather aggressive derivatives that don't necessarily correspond to what the non-noisy signal would be. So you have to be a little careful with the D parts, and making KD too large is typically an invitation to disaster because you're overreacting to noise. So the last thing I want to point out, though, is that when you put this together, you get PID, which is, as I already said, by far the most used low-level controller. Low level means that whenever you have a DC motor somewhere and you want to make it do something, somewhere there is a PID loop. Whenever you have a chemical processing plant for getting the right concentrations in your chemicals, somewhere there is a PID regulator. It's almost everywhere, or in almost all control applications, PID shows up under the hood in some form or another. But I do want to point out that this is not a one-size-fits-all. We can't guarantee stability with a PID regulator. Sometimes it's not enough. In fact, when we go to complicated robotic systems, the PID regulator will typically not be enough by itself. So we need to do a lot of more thinking and modeling to use it. And at this point, we actually don't really know how to pick these gains. However, I want to point out that this is a very, very useful type of controller. And since it is a feedback law, because it depends on the error, it actually fights uncertainty in model parameters in a remarkable way. And feedback has this remarkable ability to overcome the fact that we don't know gamma, we don't know C, we don't know M, but still we seem to do well when we design controllers for a wide range of these parameters. So having said that, let's hook it up to our car. And in fact, we had a PID regulator for velocity control on the urban challenge vehicle, Sting 1 as it's called. And we had this model that we've already seen, and I picked completely random and arbitrary numbers here for the parameters, and I even put R equals to 1, so we're going to go 1 mile per hour. Let's say 1 meter per second, it really doesn't matter. But these are arbitrary values, just so you'll see what's going on. So if we start with our friend, the P regulator, so we have Kp equals to 1 here, and all the other gains are 0, then, well, we don't actually make it up to 1. We only make it to 0.1. This we had already seen. So the P part by itself was not enough to both be stable and achieve tracking. Well, let's hook in the I part. This is cruise controller again. Kp is 1, Ki is 1, and now we're having a very nice so-called step response, which means we're responding, we're waking up, and then we're hitting it with a step, in this case a step of height 1, or 70 if it's 70 miles per hour. So then this thing makes its way up, and it stays up there perfect. So this is actually a good and successful design right here. Now, if this is so good, why don't we make Ki higher to make it even better? Well, if I crank up Ki to 10, then all of a sudden my system starts oscillating. So this is an example of where the integral part may actually cause oscillations, which is, we should at least be aware of this fact and be a little careful when we tweak our parameters. And if we see oscillations, that is a clear indication that the integral part is typically a little bit too large. What about the D part? Well, let's add the D part. In this case, it actually doesn't matter too much. What you see here is that I had a small D part. I'm a little bit paranoid when it comes to large KD terms because they are a little bit noise sensitive. But what you're seeing here is that you're getting a faster initial response because of the introduction of a D part. But then we actually get almost a slower response towards the end. So the D part is there to drive it well up in the beginning, but then towards the end, in this particular application, having a D gain that's non-zero, it wasn't even clear if that was useful. But this is some of the thinking that goes into to tweaking PID regulators. So what we are going to do next time is we're going to go now from this rather abstract integrals and derivatives to something that we can actually implement, and we're going to see how these PID gains show up when we control the altitude of a hovering quadrotor.